So in the previous section, we talked about various figures' perimeters, and now we're going to look at the perimeter of a circle, which is otherwise known as a circumference. So if we laid a piece of string around a circle and that length was measured, we'd call it the circumference of the circle, and it can be calculated by using one of these two formulas that you probably have come across already. Circumference is either equal to pi times diameter or 2 pi times radius. So we'll get to that a little bit later on in this lesson. First off, for the circle whose equation is x squared plus y squared equals 25, which of the following is closest to its circumference? So what we want to do with this is use the circle formula to establish, the circle equation to establish the radius. What you need to know about that is that a circle that is centered at the origin is going to have a radius that we can determine from the constant term on the right side. So the way the equation is structured is that the radius squared appears in that constant term. So in this case, the radius squared equals 25, so the radius itself must be 5. And we'll work with that circle equation more in class, but that's the takeaway for today, is that the radius squared appears as a constant, and we can get the radius from there. So now, to apply the circumference formula, I can do pi times diameter, and if the radius is 5, diameter must be 10, so 10 pi, and that would be equivalent to approximately 31.4. So that's choice 3. Okay, so again, more about that equation in class, but take the radius out, use it in the circumference formula. All right, example 2, exercise 2 here. Tree trunk has a roughly circular cross section, so that's as you slice it sideways. The logger uses a tape measure to find that the circumference is 6 feet. Which of the following would be the best estimate for diameter? All right, so we know that the circumference is equal to pi times diameter. So if I know the circumference is 6, I can put that where it goes and solve for d. So my diameter must be 6 divided by pi. And if I do 6 divided by pi, I get approximately 1.91 feet. So this is still in feet. All of my answer choices are in inches. The one that is closest to 1.91 would be 23 inches, and so that's choice 2. All right, exercise 3. So we're combining straight line segments with curved segments here or curved sections here to find a total perimeter. The perimeter of the straight line part is pretty simple. You've got a rectangle, so the 17 comes down. I'm not counting that interior segment. However, because it's 12, I know that the diameter of this semicircle here is 12, and therefore the radius is 6, should I need to use it. And if I'm looking for circumference of a semicircle, circumference of a semicircle is the same as circumference of a regular circle, except you have to multiply by a half. So it's 1/2 pi times diameter. So in this case, 1/2 pi times 12. So half of 12 is 6. I get 6 pi. And if I add that 6 pi to the 12 and the 17 and the 17, my total perimeter is roughly 65. Not 66. Roughly 65 feet. So just solve them separately and then put them together at the end. All right, exercise 4. Now, before we get to exercise 4 here, this section is going to come up with a way to figure out how pi gets involved with circumference of a circle and circles in general. There is some calculus involved, but we're going to try to keep it a little simpler than that and go with a more laid back version of it. So the picture below shows regular polygons. These are all equal-sided polygons whose length from the center to any vertex is staying at 1 inch. So I started a square, 1 inch to the corner. Hexagon, 1 inch to the corner. Octagon, 1 inch to the corner. Decagon, 1 inch to the corner. 15gon, 1 inch to the corner. So what should happen is the perimeter should approach the circumference, or 2 pi, because the figures are getting more circular as sides are added. And you can see this 15gon is nearly circular already. The more sides I add, the harder it would be for you to even tell that it's a polygon and not a circle. So if we use some right triangle trigonometry, we can work through this. So shown below, we have a 10-sided figure from above. Related isosceles triangle is drawn next to it. Determine the perimeter of the decagon. So first thing I want to do is figure out what this angle is that is formed by these two radii of 1. All right, so I have this triangle drawn separately. My theta has been split in half by this dotted line, and now it's alpha. And so first off, I know that the theta from the decagon is going to be 360 divided by 10. So that's 36 degrees, which means that the alpha in the triangle must be 18 degrees, just dividing the 36 by 2. Okay, now I'm looking for the perimeter of the decagon, which means I need this whole base segment here. But remember, that dotted line split the isosceles triangle in half. So what I could do is take the 18 degrees that I know alpha is equal to and solve for x by doing a sine equation. Right? This is my opposite side. This is my hypotenuse. So I can do sine of alpha, or 18 degrees, is equal to x over 1. So that means that x is equal to sine 18. That's just the 1 times the sine 18. And so that tells me that the base of that triangle would be equal to 2 sine 18. And why do I need the base? Well, because that base is this segment right here in the decagon. There's 10 of those, so that tells me that the perimeter of the decagon must be 10 times 2 sine 18. Right? Because there's 10 sides, each of them is 2 sine 18. If I multiply all that out, I get 6.18. Okay, so that's just an exercise for a decagon. Now, to show that any perimeter of these regular polygons with a distance from the center is given by this formula. It's a nice formula to know, but what's going on here is the angle that I'm inputting for sine is half of the central angle. Well, the central angle is 360 over n, so half of that must be dividing by 2. So we just put an extra 2 in the denominator, and this component right here, that's my central angle divided by 2. That's the alpha from this separated triangle. All right, so the 2n part, the reason we do that is because, remember, we doubled it, because when you solve for this half angle, you get half the base. When you put this 2 on it, now you have the whole base. And then when you multiply it by n, that's what this 10 did. It multiplies by the total number of sides in the polygon. So that's the basic explanation for it. You can copy down, you can pause and copy down this text here, but that's really what's going on with that formula. Now in exercise 7, we can use that formula from exercise 6 and just fill it in with a 5, a 10, a 50, a 100, and a 200, respectively for n. Just put it in both spots and calculate it. And what's happening is it's increasing, but the amount it's increasing by keeps going down. At the end, it only increases by 1/1000th. So if you put 2 pi into your calculator, that's approximately 6.283. We were trying to get this. Remember, as I increase the number of sides, it becomes more circular. So we would expect it to get pretty close to 2 pi, which is the circumference of a circle with radius 1. So what's happening here is as the number of sides increases, as the n goes off toward infinity or gets really big, it becomes more and more circular. And so the circumference or the perimeter goes closer to 2 pi. Actually, I should, instead of writing c there, I'm just going to write perimeter. The perimeter of this polygon, whatever polygon we're doing, 200 sides, 500 sides, whatever, gets closer and closer to 2 pi until you can't really tell the difference. And so that would be like a circumference. The more circular it gets, the closer it gets to 2 pi.